All right. Good evening, everyone.
Cough, cough.
Cough, cough. Yeah. Well, we had a lot of people ask us on Facebook whether it's going to be clear enough to use the telescope tonight. And we pretty much decided it's not clear enough. It's almost not clear enough to breathe at all. Really, the main concern we have about using the telescope on a night like this is the ash fallout that you've all seen on your various cars, I'm sure, over the last few mornings. Ash is an abrasive, and if it gets on our primary mirror of the telescope, it's probably just not a very good thing. And it's hard to clean off without damaging the coatings, and you certainly don't want it to just sit there either. So in order to avoid that type of problem, I think we'll have an alternative program tonight. So we have a couple of things. Actually, before I switch to Gerald, I'm going to share the wide field view here. Hold on for a sec here. There we go. So you can see our whole observatory here now. And this is Nellie behind me, the 36-inch research reflecting telescope. And the waving light way back in that corner, socially distanced light many feet away is Gerald McKeegan. And we enjoy coming up here every Saturday night to provide some type of program related to astronomy and hopefully using our telescope. But tonight it will just be a couple of talks. Gerald has an interesting presentation on the internals of this telescope and has prepared photographs and a discussion of what's inside this beast. And I have a presentation on this year's Royal Greenwich Museum Photography of the Year contest. And we'll get to that in a little bit. So I guess,
Yeah, why
Gerald,
don't you
take it away? Yeah.
switch camera views there. So
There we go.
there we go. All right. Well, first of all, it's my understanding that we have a number of students from a couple of different campuses in the Bay Area joining us tonight. So welcome everybody. We do this every Saturday night, starting at 9 o'clock. Hopefully the weather's going to cooperate with us next Saturday and the smoke and so on. So please stay with us, and we'll be looking at lots of exciting things with the telescope. But since we can't view tonight, we thought rather than looking through the telescope, we would look at the telescope and tell you a little bit about our telescope here at Chabot, the one that you see behind Richard. That's Nellie. It is our 36-inch telescope. And Nellie is on a fork mount, an equatorial fork mount. And I'm going to show you a couple of diagrams here and some internal views of Nellie. So bear with me here while I share my screen. And there we go, I think. And there we go. All right. So this is what the observatory complex here at the Chabot Space and Science Center looks like under better conditions. When we have actual blue skies and clear skies and so on. We have 3 observatory telescopes. The one in the small dome that you see on the left there, that's our 8-inch refracting telescope. That's the original Oakland Observatory telescope. It was built in 1883, and it still works great. In the big dome is our 20-inch refractor that was built in 1915. And then hiding over here on the right is our 36-inch reflecting telescope. That's Nellie there. Nellie is in a different type of observatory building. It's a roll-off roof building. So when we are observing, we roll the roof all the way back. There's a frame behind the building, and the roof actually sits on that frame. And we are completely exposed while we're observing with the telescope. So here's a couple of pictures of Nellie in action. You can see the configuration. Like I say, it's a fork mount. So you see the fork right here. That fork is aligned so that the east-west axis of rotation is aligned with the Earth's axis of rotation. And by doing that, we can keep the telescope pointing at an object and compensate for the Earth's rotation. The direction I'm going to show here, this is the western direction going this way. And by rotating the telescope toward the west at the same angular rate that the Earth is turning, and by having that axis of rotation parallel to the Earth's rotation, we keep the object centered in the field of view of the telescope. So just a couple of action shots here, some things that you see on the telescope, these long tubes here. We call them finder scopes, although this is a computer-controlled telescope. So generally, we don't have to do a lot of finding with the finder telescopes, but occasionally we do have to align the telescope or synchronize the telescope with the computer, and the finder scopes are handy for that. Also, if we're doing astrophotography, we'll have a camera on the main part of the telescope, and we'll use the finder scopes to see what it is that we're actually photographing. In fact, you see in this image here, which is a staged image for a TV article that came out a few years ago, you see one of our astronomers here, that's Conrad Jung, mounting the camera onto the telescope. And you see yours truly sitting here operating the computer. And this is not at all the way we actually do it. Way too much light here. We like to do those things when it's pretty dark. But, you know, to take pictures, you need light, right? So anyway, it is a 36-inch Cassegrain reflecting telescope. Reflector means it uses mirrors instead of lenses. And I've got a kind of a cutaway diagram here to show you what it looks like on the inside. This is a very simplified block diagram, if you will, of what the telescope looks like on the interior. So there are two mirrors inside. The primary mirror, which is at the back of the telescope, is 36 inches in diameter. The glass for the mirror is about 5 inches thick, and you'll see that in a few minutes here. And the primary mirror has a slight curvature. It's a concave curvature. The actual curve is called a parabolic curve. For those of you who are into mathematics, it's a parabola or a section of a parabola. And the secondary mirror is in the front of the telescope. That's this mirror up here. And you notice that it's curved in the other direction. It's a convex curvature on that, and I'll show you why that is here in just a second. So what happens is the light comes in the telescope from the front of the telescope, hits the mirror in the back of the telescope. Because that mirror is curved, the light bounces off of it, not straight back, but it bounces off in a cone of light, and that cone of light hits the secondary mirror. Because of the convex curvature of the secondary mirror, the light bounces off of it also in a cone, but in a less steep cone that comes off the primary mirror in a fairly steep cone of light, comes off the secondary in a less steep cone of light, which then projects down to the back end of the telescope where the focal point is. And then, of course, we put either a camera or an eyepiece at the focal point, depending on whether we want to look visually or if we want to take pictures with the telescope. So that's the basic diagram of the interior of the telescope. But I thought it'd be interesting if you could actually see the interior rather than us trying to move the cameras all around here. We have some pictures from the last time we cleaned the telescope. So here's an image getting ready to disassemble the telescope. We've tipped it down to where it's horizontal. And you can't see it very well, but we've attached a hoist to the back end of the telescope. And we're going to remove this back plate, and the primary mirror is attached to that back plate. Everybody has their mouth open. Yeah, I think you're muted there, Richard.
Sorry, I was saying that everyone looks like they have their mouth open.
Yeah, this can be a kind of a hair-raising thing. The assembly that we're about to pull out weighs almost 800 pounds. and it's hung by one little hoist, and it makes us all a little nervous when we're doing that. But here you see it starting to come out, and you can see the mirror right here. This is the mirror, and you see how thick it is. It's about a 5-inch thick piece of glass, which makes it nice and sturdy and very stable as we're observing over the course of the night. But it does present a problem if it's warm in the daytime. We've had some 100-degree, 95-degree days here in the last few weeks. And when that happens, the mirror gets, the glass gets very warm, and glass takes a long time to dissipate heat. And so that can be a problem for us if we're observing. If the mirror is warmer than the surrounding air, it creates a disturbance right above the surface of the mirror, and you get a boundary layer that's much warmer air. And if you can imagine looking across the hot parking lot, asphalt in the parking lot, and seeing those ripples of air that you see, that's what we would get when we're looking through the telescope. So we actually have fans mounted. You can see one of them right here in one of the previous pictures. In fact, I can go backwards here. One more. Keep going. There we go. So here's one of the fans. You see all three of them right here. Those fans are positioned so that they blow right across the top of the mirror. Excuse me, right across the top of the mirror to create what we call laminar flow across the mirror to keep it from that warm boundary layer from forming. Now I got to work my way back to the slide.
Yeah, what a lot of people don't realize, if a mirror gets warm from the daytime temperature, it may not cool down to the nighttime ambient temperature till midnight, 1, 2 in the morning.
Yeah.
You can end up losing half the night to thermal aberrations in your view because it gets too hot during the day.
Right. So the fans help. Doesn't eliminate the problem, but it does help. It gets that warm boundary layer blown away. It also helps to cool the mirror, but it does still take a long time for the mirror to cool.
We do not use Windex.
Yeah, no.
Not good for the optics.
Yeah. So here's the mirror pulled all the way out. You see the mirror, the primary mirror right here, and you can see it's very dirty. This was when we were getting ready to clean it. And you notice it's quite a bit smaller than the back plate. And there's two reasons for that. One is that the internal structure of the telescope is very robust. You'll see that in a minute. But the other reason is that when this telescope was designed, the original design was for a 1 meter mirror. Now this mirror is 36 inches in diameter, which is about 3 1/3 inches smaller than a 1 meter mirror would be. However, we were going to have to pay to have a 1 meter mirror made for us, and then we got a good deal. We were contacted by the Lawrence Livermore National Lab. They had a 36-inch mirror sitting in a box in a warehouse that had been purchased for one of their nuclear testing programs, and they ended up never using it. So it was a pristine mirror sitting in a box, and they said, we'll donate it.
Well, we hope they'd never used it. Have we taken a Geiger counter to it anytime recently?
So anyway, they donated, so we just adapted the telescope to a 36-inch instead of a 1 meter mirror. It's a small difference in size, but not real significant. Now you see this long tube, which was not in the diagram I showed you. This is called a baffle. One of the problems that you have with telescopes, especially big telescopes like this, is that when you point it at the night sky, you're looking at some object like a star or a galaxy or a star cluster or something like that. But there's other light from the sky, like sky glow. And if you're looking near the moon, you'll get some moonlight that shines at an angle into the telescope, and it bounces around in the telescope as stray light. And that stray light can cause some problems. It can cause the contrast between the dark sky and the stars that you're looking at to be reduced. And so to get rid of that stray light, we use baffles inside the telescope. There are different ways of doing that, different ways of baffling a telescope. This one has that baffle tube that's right in front of the primary mirror, but it surrounds the hole in the primary, which is where the light from the secondary gets down to the eyepiece. So that is to prevent stray light from getting down to the eyepiece. So
we have an interesting question. The question was, how do we make sure the telescope is, I guess he's really asking, how do we make sure the telescope is collimated? And how do we get it aligned? And what tools do you use through the eyepiece?
All right, that's actually a good question. And you see part of it right here. If you notice these screws where we bolt the back plate into the tube of the telescope. I'm going to back it up here a little bit. You see some bolts here. These are big bolts, but next to it are two small set screws. And those set screws actually allow us to adjust the gap between the tube and the back plate. So that allows us to actually make fine adjustments to the positioning of the mirror. When you have a telescope, you want the primary mirror and the secondary mirror to be exactly parallel to each other and exactly centered on each other. And that process of getting them parallel to each other and getting them centered is called collimation. And there are a couple different ways we can do that with this telescope. We can adjust the back plate here, which adjusts the mirror, makes small angular adjustments to the mirror to get it parallel. And then the secondary also has some adjustments on it that allows us to get it parallel and also to get it centered on the primary mirror. Hopefully you design it so that they're pretty well centered, but you do have to make some minor adjustments when you're collimating the telescope.
When you're collimating it at the eyepiece, do you use an artificial star? Do you use a star or laser collimator, or just eyeball it?
We use a star. We point it at a star to get it lined up. And what you do is you point it at a bright star, medium bright star. With a big mirror like this, you don't want to point it at something like Vega. It's too bright. But magnitude 2.5 or 3 star would be just right. And then you crank the telescope out of focus. And when you take it out of focus, instead of the star being a point of light, it becomes a donut-shaped image of the star. And it has a dark center, and then it's a bright ring, kind of like a donut. And if the telescope is properly collimated, the dark center circle is precisely positioned in the center of the donut, and it's not twisted or distorted in any direction or anything like that. It's not off center. And so that's how we go about collimating the telescope. So that's what we're actually looking at while we're making adjustments to the mirror.
How often do you go through this cleaning process on Nellie?
Ideally about once every 2 years.
And do you clean the secondary as well?
Yes, but it's a little bit less elaborate of a process. We just basically kind of spray some distilled water on it, rinse it off. Because the secondary faces down when we're observing, it doesn't collect nearly as much dust as the mirror, which is facing, or the primary mirror, which is facing up when we're observing. So it's a much less challenging task. You see how much dust collects on the primary mirror, and a little bit of dust is okay, but as it builds up, we start losing some of the ability to see really faint objects. Then we start noticing that things aren't as bright as they should be, and just by visually looking at the mirror, we can tell it's time to get it cleaned. So one last slide that I wanted to show you. This is looking back up the tube. You see the internal structure of the tube. It's very robust. The entire telescope assembly weighs 14,000 pounds. So this is a lot of weight, and so it has to be structurally very strong. Now that includes the weight of the fork mount as well. So it's a pretty robust telescope. But you see right here, this is the secondary mirror. It's mounted on what we call a spider. These three legs here are the spider. The blue tarp you see, that's just the cover that we keep over the telescope when we're not using it, and we don't need to take it off when we're cleaning the mirror, so we left it on. Normally, when we're observing, we take this blue cover off, and that's the front end of the telescope there. But this is the secondary mirror. You see it also has a little bit of a baffle around it. And it's in this picture, you can tell it's much cleaner than the primary mirror. We haven't cleaned it yet, and already you can see it's much cleaner than the primary was. So that's the internal structure of our telescope. And
That's cool.
Hopefully,
thanks for that. There's a couple more questions,
okay.
And I wanted to make a couple comments as well. Alan pointed out that Ken Swaggerty is a master in collimating Nellie, and Ken's son Joe is joining us tonight on this presentation.
Oh, okay.
I said there can't be that many Swaggertys out there, and so anyway, welcome to all of you.
Is Ken going to train Joe on how to collimate the telescope?
Well, maybe that's a good idea. Joe, you'll have to get back to us on that. The other question. This is kind of a general telescope question. I get this question a lot with all different kinds of telescopes is how far away can you see through this telescope? Well, the thing about telescopes is, they're big light buckets. So a bright thing, whatever it is, that's tens of millions of light years away will be visible in Nellie, and it will also be visible in a $100 Sears telescope. But in Nellie, you're going to see a lot more magnification, and you're going to be able to see a lot more resolution, a lot more detail, and if you're lucky, you may see some color as well. So it's not a matter really of how far away you can see, but can you get down to very dim magnitudes through a telescope? And that's what distinguishes a telescope like Nellie from something that's a store-bought telescope or a pair of binoculars or something like that, is the ability to look at very dim objects. And of course, the dimmer the object, there's a good chance it's also farther away. Not always, but often that's the case. So I'd say that through Nellie, we've seen galaxies certainly tens of millions of light years away, possibly hundreds of millions of light years away.
I have an official.
Yeah. Go ahead. What'd you say?
The most distant object we have imaged with this telescope was 9 billion with a B.
So you were looking at a quasar.
9 billion light years away. Yeah, it was a quasar.
Great.
Yeah. So, yeah.
I was about to say, if you happen to see a quasar, then you win the contest.
Yeah. If it's bright enough, you can see even things like quasars. Quasars are extremely bright. They're young galaxies with very active black holes at the center, and they are extremely bright, and so you can see them from a very long way away.
Cool. The other thing I wanted to point out is some of you who've been around telescopes, been to star parties, maybe looked at telescopes in magazine ads or photographs, probably have seen smaller versions of this design on people's personal telescope mounts. And Celestron makes a whole line of what are called Schmidt-Cassegrain telescopes. Now, this telescope is a classical Cassegrain. It's got the primary mirror that Gerald described, and it's got the parabolic secondary mirror that Gerald described. A Schmidt-Cassegrain, which is a commercial version of this type of telescope, has a third optic on it, and it's basically a plate, a glass plate that covers the entire front. So in front of that secondary, move your cursor right there, right, going all the way up and down, would be another piece of glass that has a funny shape, and that shape allows the secondary, instead of being parabolic, to be spherical. So
and the primary
and the primary becomes
right,
spherical as
right.
well. So it makes it less expensive to manufacture the optics. All you have to do is make that funny shaped corrector plate. And of course, the other advantage is it prevents the primary mirror from getting dirty as often. So you don't have to clean them as often. So they
Right.
make for very good consumer telescopes.
Yeah, yeah. So just to clarify, it's the primary mirror on in a classical Cassegrain. The primary mirror is a parabolic curvature. The secondary mirror is a hyperbolic curvature. So it's that for most people an insignificant difference, but it to be pure here, we ought to say the secondary is hyperbolic.
All right. Very good.
So, all right. Any other questions?
Steeper curve.
Right, right. Any other questions?
About the telescopes? No, not at the moment.
All
I'm
right.
sure there will be more.
All right. Well, you had something you want to talk about.
Yeah, I did. Let me get my screen share going here. Here we go. All right. Well, every year there is an astrophotography contest sponsored by the Royal Greenwich Museum in London. And I thought some of the photographs from this year were interesting to look at. And one of them is somewhat controversial. And I'm curious about Gerald's opinion and other people's opinions. But I'm starting with the non-controversial one. And this one, and let me get the name of the person because I really have to be nice about making sure I get people's names. This was by someone named Alexandra Hart. And she took a picture of the sun. And what I found interesting about this was it was done with a C11, a Celestron 11-inch telescope, and very similar in design to what I was discussing just a few minutes ago. It's a Schmidt-Cassegrain. It was on a Orion EQ6 mount, which is a standard commercial mount. It's available actually here in the Bay Area at the Orion store. And what's called an ASI CMOS camera, which is a standard astrophotography camera. What is interesting about this is that it's at F50. So she had some kind of focal extender on there. I'm actually thinking of writing the photographer to find out exactly how she was able to extend it out to that degree, possibly with an eyepiece in front of the camera, possibly with some other sort of focal extender. And the exposure time is only 8 milliseconds. Because it's the sun, you can't take a long photograph of the sun and expect to get anything. So there's also a sun shield on the front of the telescope that prevents, most of the energy from reaching the camera. Otherwise, it would just burst into flames. So I thought this was pretty tremendous. I've never seen this degree of detail from a C11 before of a solar photograph.
Open it up so we can see it.
You're not seeing the photograph?
Nope.
Oh. Hold on, let me try restarting the share. I don't know what you were seeing then.
We just saw your Explorer.
Okay, are you seeing it now?
There you go. There you go.
All right, there we go. Good. Sorry, I was talking about it. I thought everybody was seeing it. Yeah, so what you could see here is what are called faculae. Yeah. And it's the typical surface feature of the sun. And each of them are essentially, each of those little funny shapes, they're little squares and rectangles and triangles. They're basically thermal artifacts from all this roiling gas that's coming off of the sun. And they're very short-lived. It's constantly changing and moving around. But to capture that on an amateur instrument, I think is fantastic.
Yeah, if you could think of boiling water, if you're looking at a pot of boiling water, you see bubbles rising and popping at the surface. This is essentially the same idea. Interior to the sun, you've got a very convective layer, and hot gases in that layer rise up and sort of pop to the surface. And this is going on all the time. And that's what all these little faculae are, just hot gas popping up to the surface of the sun.
Okay, let's take a look at the next one. Now, Gerald, I really was interested in your opinion on this one. So the moon has very subtle color, and it never looks like this to the eye. So what this photographer did was take a color CCD and take many exposures of the moon using different filter sets to separate those colors out, and then enhanced the degree of color that is visible in the final result using whatever astrophotography processing tools he preferred to use. So that way the different minerals that were on the lunar surface would be distinguishable from one another. And I cannot speak to the accuracy of this image at all, other than, it's quite interesting to look at. It does look like, from what I've heard from you and others, that these different regions next to the seas do in fact have, like there's more basalt in one area and there's other
Right,
types
right, right.
of minerals in others, and they're all showing different colors. I couldn't speak to the accuracy of it, but they thought it was very interesting. Let me get the.
Yeah. The bright crater that you see down and to the left, that's Tycho.
Mhm.
And then you can see the ejecta rays extending out from Tycho. The highland region around it is an older part of the moon, whereas the mares, you see a couple of the mares,
Mhm.
the dark blue regions in the upper
Over
part of the image.
here
Right,
and over
right,
here. Yeah.
right. So those are lava flows that have oozed up through cracks in the crust and filled basins. Whereas the mountainous region around Tycho to the right of Tycho and so on, those are what we
Yeah,
call
all
the
of this.
highlands,
Yes.
and you get a lot of what's called a northosite, which is a mineral that you find quite a bit on the moon in the highland regions.
Great.
And
The name of this photographer, by the way, is Alan Pelou. It's important.
I suspect what he did was did a little bit of false color stuff to
Mhm. Mhm.
apply different colors to different shades of dark gray and so on
Yeah,
to produce those effects.
I
And it,
suspect you're right. Yeah.
yeah, and it's interesting to look at this because anytime you do something where you can increase the contrast between different regions, you get a better understanding of what's old and what's new, and where are there different types of mineral deposits and so on. So it's informative, but he did fudge. so,
Yeah, that's right.
so
All right. Well, this one wasn't fudged. I thought this was really nice. This is I'm gonna botch this name. It's Lukasz Sushka. And just like last week, we had a great conjunction of the moon and Mars. This is a earlier conjunction of the moon and Jupiter. Of course, Jupiter being over here, moon being over here. And he had a very nice night to work with, obviously. Jupiter looks very steady in that image. And I just thought it was well done.
all right.
See what else we got here. Okay, this
Ah,
one yeah, this is cool because it was taken by a 10-year-old, and that's just awesome. And her name is Alice Fock Hang, and it's done with a Nikon D610 DSLR camera, and it's 18 13-second exposures stacked.
she was somewhere farther south.
Yeah,
But you can see more of the central bulge.
that's right. It probably helped me. It could have been.
Hawaii,
It could
Hawaii.
have been Hawaii. It could have been in South Asia. Any number of
Yeah,
possibilities.
because
I
you
don't
can
know where
see the
she's from.
horizon, and the horizon is absolutely flat. So I'm suspecting that she was somewhere where she was looking out over the ocean.
Well, what's noticeable to me about this photograph is the focus is absolutely dead on
Yeah,
this. I mean, the stars are absolute pinpoints, and that's the hardest thing to do. And it's actually double hard to do sometimes with the DSLR camera, because a lot of people make the mistake of just turning the lens to infinity and shooting away. And actually, when you set your lens to infinity, you've set it to infinity and beyond.
Yeah.
And it's usually a little too far, and you have to move it back a little bit.
Right,
So
right.
she really took great care in somehow evaluating the focus to get this excellent composition and shot.
Yeah, one of the things that a lot of astrophotographers do is they will take their camera lens and spend a lot of time just pointing at one star, getting the focus absolutely perfect, and then they will take a piece of tape and put it on the lens to show what the true infinity position is, and it's often slightly off from what the camera lens says it is. So it's a technique we use often.
That was my trick during the solar eclipse.
Yeah. Yeah.
And focus on a sunspot, and don't forget where you focused.
Yeah.
And because you don't want to be wasting the eclipse focusing. All right, what do I have next here? All right, I think the next one might be my controversial one. Okay, and you'll see why it's controversial.
Yeah, just for people, anybody who's come in late, the reason we're showing images and not looking actually through the telescope is because we are bathed in smoke up here at Chabot right now because of all the fires in California and Oregon and Washington. And we are just not able to observe with our telescope right now. So we figured we'd show you some cool pictures that were taken by other people.
Okay, so this is the controversial one. All right, so this is a very strange photograph, I think. I think it's interesting. I'm not sure I like it, and I'll tell you why I'm not sure I like it. So first of all, and this is the Andromeda Galaxy, and you see the Andromeda Galaxy in this main oval in the center here of the image. All of the foreground stars in the Milky Way that you normally see alongside the Andromeda Galaxy when you're viewing through a telescope have been blurred in this funny way. And the way he did this was the optics. He had a tilt mirror inside the image train of his telescope, and he was able to tilt the mirror back and forth while shooting the image. So everything that's in the center of the image, in where my cursor is, but to the left and to right, left and right, is in focus, and everything that was above and below that area is out of focus because that's the part that was getting tilted. And it kind of gives this strange, I don't know, snow globe effect to Andromeda.
Really dirty lens.
My first reaction to this is, oh my God, he really needs a field flattener, or something, and then I realized that this was intentional, and I was kind of offended by it because we spend so much time getting focus right when we're shooting deep sky objects that to intentionally put it out of focus was like, oh my God, that's blasphemy. How can you do that? So I just want
the real question is why.
Well, it was some of these photography contests have now become more oriented towards the art of photography and the things you can do artistically with the lens or the camera or the telescope than necessarily a standard scientific image or catalog image of whatever it is you're trying to shoot. Now, I want to show you a comparison to an Andromeda image from a local astronomer who we had the fortune of having him talk to us a few months ago. And this is Andromeda, and everything is focused all the way out to the very edge, right? So here's Andromeda and, the companion galaxies, and clouds of gas in space surrounding Andromeda, or at least in the same field as Andromeda. This is from Rogelio Bernal Andreu, who lives here in the Bay Area. And just to compare that with the previous one. I prefer the second one myself, but but this is interesting, and it may not be for everybody. But it was considered the winner of the entire contest.
Really?
So, for what it's worth, and
Okay.
that's the Greenwich Observatory. So you can't, it's the Greenwich Observatory. So you have to take it with some degree of seriousness.
Yeah,
But
those people never know what time it is anyway.
yeah,
So
right. That's right. It's always like 9 hours off.
yeah.
All right, that's all I got for the photographs.
Okay. Well, let's see if there's any questions. We apologize we're not able to look through the telescopes tonight. Mother Nature and whoever started these fires is just not cooperating with us tonight.
One person wanted to see that photo of the sun again. I will oblige them. Hold on, let me back up here. There we go.
There you go.
That was the one with the faculae of the sun using a Celestron C11 telescope.
Speaking of Celestron C11s, I'm going to back away from me here. If you kind of put me back on the screen.
Yep.
I've got a Celestron C8. Look at this right here. All right.
It's an old orange tube version. It's a classic.
Original orange tube Celestron C8. The 8 stands for the diameter of the telescope. It's an 8-inch telescope. A C11 that Richard was talking about is an 11-inch diameter telescope. We rate telescopes by their size, not by their magnification. So when you hear astronomers talking about different telescopes, you will often hear them refer to the telescope diameter. Our big telescope, the one behind us here, is a 36-inch telescope. The one I just showed you is an 8-inch telescope. The biggest telescopes in the world right now are 10 meters in diameter, 33 feet. And they're working on building one that's going to be 30 meters in diameter, 100 feet in diameter. So, that's how we talk about telescopes, is by the size of their mirror or the size of the aperture, the opening in the front.
Okay, and that feeds into Jasper's question. Thank you for clarifying your question, Jasper. He's the one who I thought had asked about collimation, but in fact, what he was getting at was, is it a problem that the secondary mirror has to block the very center of the primary mirror?
Good question.
It is.
Why don't I go back to my thing here?
I'll let you get that one.
Okay. And we'll get that going here. Come on. There we go. All right. So this is a cross-section diagram. And so what you got to think about is that each of these two lines that you see here represent a view of the same object, okay? Way out in space, so far away that when you look at it, the lines to it are basically parallel coming from the telescope. Each of these is an image of the same object. So maybe there's a planet out there and we were looking at the planet. So this line is a view of the planet. It's what this part of the mirror sees. This part of the mirror is seeing the same view of the planet. So both of these are reflecting the same view of the planet to the mirror, secondary mirror, and then back to the same point at the focal plane. So every point on the telescope or on the primary mirror that can see out the front of the telescope is basically taking the same image and stacking it, if you will, at the focal plane.
Or combining it might be the better.
Yeah,
combining it into a single image.
Yeah, but you don't want to think of it as this part sees one corner of Jupiter and this part sees another. They both see the same view of Jupiter, and they just bring them together so that you're adding all the light that both points can see to form the final image. Now, obviously, where the secondary is, it's blocking the light from getting to the primary, so you don't get anything from there. But because all the other points, individual points on the mirror, see the same view, they fill in the blank, if you will, of where the secondary would be. So when the telescope is in focus, you don't have a central obstruction. You don't have a shadow in the middle of the image. Um, if you crank the telescope out of focus, like we talked about a while ago when we were doing collimation, then you do see the central mirror, and it does block it because now you're no longer bringing all paths of light to a focus at the same point. And that's how we do the collimation. So when the telescope is in collimation and when the telescope is in focus, you don't have a central shadow or obstruction in the field of view of the eyepiece.
Yeah, and the other thing to realize is if you think about the area of a circle, right? The vast majority of the area of a telescope mirror is the area alongside the edge of the mirror. So the center, even though it's being blocked, it only accounts for a small percentage of the overall surface area of the mirror. And so although it does subtract from the available light gathering capability of the primary, it's not enough to make a significant difference.
Right. And the thing that's important about the large size of the primary is that the bigger it is, the higher the resolution you get in your images. So when you crank up the magnification, you can still see lots of detail. Whereas a smaller primary mirror, the same magnification, you don't see as much detail. Now, one other thing that's kind of interesting, as long as we're talking about this works as long as the curvature of the mirror is perfect. If there are any aberrations in the curvature of the mirror, then you get light bouncing off of it going to the wrong place. And that's actually what happened with the Hubble Space Telescope. When the Hubble was first launched, they made an error in the curvature of the mirror. And what happened was that just the outer edge of the mirror was not the right curvature. So what happened is light hitting that outer edge was bouncing into a different place at the focal plane. And that caused the whole image to look fuzzy. And so they had to correct for that. They corrected for it, not by correcting the mirror, but by putting basically corrective lenses down here at the focal plane to bring things back into focus. So that was a very frustrating experience when they first launched the Hubble Space Telescope. They were expecting these pristine, beautiful images, better than anything they'd ever seen before. And the first images that came down were a little bit fuzzy. And after doing some research and looking back at the records for when the mirror was ground, they discovered that they had made a mathematical error, which caused the outer edge of the primary mirror to be at the wrong curvature, making everything fuzzy.
That was a great save.
Yeah.
To build those corrective optics and get them installed.
And
It's because of the advanced computerization of optical ray tracing that you were able to reverse engineer the blurry image that they saw and figure out exactly what was wrong with the primary mirror based on looking at a star and understanding exactly what would cause that pattern of defocusing.
And just for grins and getting a little bragging rights, the company that made the corrective optics is right here in the Bay Area, Tinsley Labs over in Richmond. They made the corrective optics that astronauts installed in, I believe it was 1993, to fix the Hubble Space Telescope. So if you ever happen to drive by Lindsay or Tinsley Labs, say hello. Wave.
Yeah.
Say thank you.
they are also the lab that is responsible for the figuring of the James Webb telescope mirrors.
Yep, and they did the rework of the primary mirror on Nellie. When we got it from the Lawrence Livermore lab, they had to refigure it, and it was done at Tinsley. So
yeah, we're lucky to have them around.
Yeah.
Another question. I'll take this one. What's a good green laser for pointing out stars when stargazing? Okay, so I always answer that question with a caveat, which is there is actually no such thing as a good green laser. But
Right.
if you need to use one, if you absolutely need to use one for, a scouting trip or something where you really want to point out constellations or planets or whatever, green laser pointer can be useful. And company in the Bay Area that sells them is Orion Telescopes. Theirs are particularly resilient and rugged. I always warn people that if you're in the city, you generally don't want to use a green laser pointer pointed at the sky. The FAA does not take kindly to that. And if you are at a star party or around other astronomers, some of them are doing astrophotography and they don't want your green laser beam passing through the middle of their images. So if you are going to use one, be very considerate and be very careful where you're using it.
And no more than 5 milliwatts.
Yeah, no more than 5
Right.
milliwatts. That's right.
Right. It's extremely important that you be safe with those green lasers. You don't point it at each other. You don't point at anybody's face, and you definitely don't point it anywhere near any airplanes. You can be arrested for pointing a green laser at an aircraft. So
Yeah, and
be forewarned.
deservedly so.
Yeah.
Yeah, don't want to do that. Pilots don't like it. Here's a more of an astronomy question. On December 21st, there will be a conjunction of Jupiter and Saturn, where Saturn and Jupiter are going to be very close to one another in the sky.
In the same field of view.
In the same field of view. What is the significance of this, and are we doing anything special for it, Gerald?
Well, the significance is mostly that because Jupiter and Saturn don't orbit at the same rate, Jupiter is closer to the sun than Saturn, so it orbits faster than Saturn. Jupiter takes about 12 and a half years or actually about 12 years to orbit the sun, whereas Saturn takes about 30 years to orbit the sun. So Jupiter laps Saturn periodically, and basically that's what's going to happen in December is Jupiter is going to lap Saturn, and there will be one day when they will be close enough in our line of sight so that they appear in the same field of view of a telescope. And it's real important to understand they are not physically close to each other. In fact, they're more than 400 million miles away at that point, but they're in the same line of sight. So, if you imagine you hold two fingers in front of you, one farther away than the other, but if you put them, to where they're both overlapping each other, they look like they're touching, but they're actually very far away. And the same thing is true with Jupiter and Saturn on that night. Now, unfortunately, by that time, by late December, Jupiter and Saturn are going to be very far over in the western part of the sky.
It's going to be tough.
So they're actually going to be too low. By the time it's dark enough to see them with this telescope, they will be too low for this telescope to view it. So we would not be able to do it as part of our Saturday night viewing or anything like that. However, we are going to try to take photographs earlier in the evening with this telescope and try to at least get a picture to show you if we can't show you a live view through the telescope. So stand by. Everybody hang loose until the 21st of December.
Let's see. Oh, thank you, John. John Fang answered this question partially. The question was, is Nellie larger than other telescopes in the Bay Area? I would say Nellie is the largest public telescope in the Bay Area. Obviously, the scopes in the main, especially the main instrument at the Lick Observatory, is a larger telescope. It's used.
Yeah, that's a research. Yeah,
that's a research telescope. What's the size of the mirror on that? It's 100.
They've got a couple of them up there. The old refractor is 36 inches. The
Yeah.
same size
No, I was talking about the reflector.
But I think they got a 1.5 meter or something like that up there, and they've got a couple of them. So I don't know the sizes of all of them, but I should point out there is a telescope, a publicly available telescope in the Bay Area that's a little bit larger than this. It's 40 inches in diameter. It's a Dobsonian telescope, and it's up. I forget the name of the park now. It's up near Sonoma.
Oh, it's I know what you're talking about.
Yeah.
It's in the Valley of the Moon. Yes.
Yeah. So it's a state park up there. They have an observatory, and they have a Dobsonian telescope, which is a different kind of reflecting telescope. It doesn't have a fork mount. It's not something that tracks and so on. But they do make it available to the public periodically, and it's a 40-inch diameter. It's a big Dobsonian telescope. So,
yeah, John had mentioned that there is a 70-inch modified Newtonian reflector in the process of being constructed.
I've been in process for about 10 years.
Well, I'd say about $120,000 have been spent in the last 12 months. So the superstructure has all been fabricated, and there's a couple of other metal fabrication pieces that have to be done, and it should be finished within the next 2 years at this point.
I'm going to hold you to that.
No, please don't. I am involved in that project, but they keep me at a considerable distance, which is wise.
Yeah. And the engineer that's working on it, he is the same engineer who designed
built this thing. Yeah. So
let's go behind us here.
So yeah, it's all in the family.
Yeah.
Let's see.
Yeah, if you got questions, folks, please fire away. We're unfortunately we can't observe with a telescope. And also, see a donate button on the Facebook page. Please, if you don't mind, give us a donation. We're up here at Chabot Space and Science Center, which normally is open to the public and normally charging admission. And we're trying to keep everything, still working, because we will be reopening as soon as this pandemic is over. And we do need your support. So if you've got a couple of bucks to spare, please click on that donate button and help us out.
Alan came up with the name of the park. It's the Ferguson Observatory.
Yeah, that's it.
And I couldn't remember it either.
Yeah.
Can you use binoculars to see the colors of stars? On some, yes. On the brighter ones, yes. So there's, with your naked eye, sometimes you see color of stars, right? So if you look at Betelgeuse, which is a star in Orion, it's very obviously a deep red color. Through binoculars, if you look at certain double star pairs, you'll see that each star in the pair is a different color. You got a red and a blue one, or an orange and a blue one.
Alberio is a double star in constellation Cygnus, and even with binoculars, you can see that one is yellow and one is blue.
That's right. Someone asked where they could see those photographs online. Let me see if I could find that real quick here.
While you're looking for that, do we have any other questions?
Let's see. What has been the most exciting event or astronomical object that has happened for you in the past year?
In the past year?
In the past year. So you got a limited time frame here.
So the 2017 eclipse doesn't count.
No, it doesn't.
Oh well. Well, Saturn is back in view, so we've been, enjoying that. I think some of you are aware that we use this telescope to track asteroids, and we've tracked some pretty interesting asteroids over the past year. Gosh, can't think of anything really unusual that's happened over the past year. I take it back. We had an anomaly earlier this year, actually starting in December and going through to about February. Richard mentioned Betelgeuse, which is a bright orange star in the constellation Orion. And Betelgeuse is normally a pretty bright star. But starting, I think, in early December of last year, it started fading. And that got everybody's attention because we know that Betelgeuse is so massive and it's so far along in its life that at some point in the next 100,000, 200,000 years, it's going to explode as a supernova. And we don't know exactly when that could happen. It could happen tomorrow. It could happen 200,000 years from now. But all of a sudden, Betelgeuse was fading and it got much dimmer. And it stayed dim for several weeks, actually about 3 months. And then it slowly started brightening again. And there was a lot of speculation about why that was happening, whether or not it was a sign that it's about to explode or what was going on. Now, eventually they discovered that what was happening is that because Betelgeuse is so large, it's a supergiant star. It's over 1,000 times the size of our sun. And because it's so old, there are periodic eruptions, if you will, of gas shooting off, just like we have coronal mass ejections on our sun. And one of these had produced a cloud of dust that had basically surrounded the star. And so that dust was blocking the light from the star, which made it dim. Eventually, that dust dissipated and Betelgeuse returned to its normal brightness. But for a while there, the astronomers were getting pretty excited trying to figure out what was going on with Betelgeuse. So that's, something interesting that happened.
Great. I actually found, I'm going to put a comment in for those of you that are asking questions. I'm going to now put the link in for those photographs. And I just did that. I hope you see it. The main website is www.rmg.co.uk. And there's a bunch after that takes you right to the page that I got those photos from, and those are in the link. So it's called the overall winners from the 2020 contest. So scroll through there and hopefully you'll see, let me see if it shows up here. Facebook, it doesn't always do exactly what you think it's going to do.
It's there. So.
Oh, you see it? Okay,
yeah,
good.
Yeah.
I'm not seeing it on my phone yet. I hope I hope the person who asked sees it. All right, let's see if there's anything else. People were commenting that that what they enjoyed seeing this year was Neowise, the comet. I agree.
Oh yeah, I forgot all about that. Yeah, Neo.
Here's one for you. Are there any interesting asteroids coming up within the next year that we're trying to?
Well, there's the election day asteroid. so there's an asteroid. It's 2018. I want to say OG or something like that. And it is going to come sort of close to the Earth on the 2nd of November, the day before Election Day. And some media folks found out about this and they made it into much more of a big deal than it really is. It's an asteroid that was discovered in 2018. And right now the prediction is that it will pass the Earth actually a little bit farther than the distance to the moon. However, because they were only able to observe the asteroid for a brief period of time in 2018 when it was discovered, the orbit calculation is not as precise as we would like it to be. And when that happens, your predicted position at any point in time is based on the nominal observation data, but because all observations have some margin of error with them, when you take into account that margin of error, there's a possibility that this asteroid could actually get a bit closer, still very much a safe distance away. But for some reason, the media has got hold of this and they're saying, hey, we got this asteroid that's going to pass very close on election day. It's actually the day before the election. And why that's getting everybody's attention? I don't know, but because there are many more asteroids that come a lot closer than that. It's pretty common. You're muted. Yeah, you're muted, Richard. Well, I'm not hearing you. Nope. No. Did you pull the plug?
No, I didn't. Let me restart my mic.
Yeah, when you talk, it shows that you're talking, but
How about now?
very faint.
That's strange.
Huh.
All right. We will switch to a different mic. How about now?
Okay.
Okay, good. I'll switch to a different mic. Okay, Giza asked a question. How can you find out about astronomy clubs in the Bay Area? Well, there happens to be a website you can go to called the Night Sky Network. And if you go to Night Sky, one word, nightsky.jpl.nasa.gov, G-O-V, you'll be taken to a web page that allows you to search by zip code and find the astronomy clubs in your area. If you happen to live anywhere near Oakland, of course, I'll give a shameless plug for the East Bay Astronomical Society. We're based here at the Chabot Space and Science Center, but there's certainly many fine astronomy clubs around the Bay Area. San Francisco Amateur Astronomers, the San Jose amateur astronomers, and San Mateo, Tri-Valley out near Livermore, Mount Diablo Astronomical Society, covering the Walnut Creek Concord area.
Sidewalk astronomers
and the sidewalk astronomers in San Francisco, correct. So anyway, a lot of choices around here. Let's see. I think that is it for the questions.
All right.
So I think that'll be it for tonight, Gerald.
I think so.
Considering the conditions.
Let you know about a couple of upcoming events. Next Friday, Chabot will be hosting a virtual hike along with the East Bay the East Bay Regional Parks District. They'll be hosting a virtual hike on Chabot's Facebook page. That'll start at 8 o'clock this coming Friday. And then, of course, Richard and I will be back next week, hopefully sans smoke, for another observing session with our telescope here. And that'll start at 9 o'clock. And then 2 weeks from tonight, we have kind of a special event. That's going to be Observe the Moon Night, and that will be observed all across the world. It's International Observe the Moon Night. So we will be doing, hopefully, if the weather cooperates, a live tour of the moon's surface with our telescope. So you want to check out that. And again, that's 2 weeks from tonight.
All right.
All right.
Thank you, Gerald.
All right. And we appreciate the donations, everybody. Please keep them coming. And we look forward to seeing you again next week.
All right. Everyone be safe, be healthy. We'll see you soon.